I am now going to be testing each of these candies for their properties when I hit them with a hammer. First off, we'll start with our gumball. As you can see, hitting it with the hammer causes it to shatter. Next up, our hard candy. Taking it with the hammer, hitting it causes it to chip and crack. After that, we have our stick gum, and even standing it up, hitting it does not really cause it to deform whatsoever. I am able to get it to crack into several pieces. Next up is our licorice. Taking it with the hammer, and it comes out relatively unscathed. This one caused a minor crack, but this licorice is also slightly old, so it is a little more dry. However, it is still quite flexible. Next up, we have our taffy. This taffy again, as well, slightly old, somewhat dry, which causes it to shatter. All that we have left now is our gummy bear, and I take him. Even with several good smacks of the mallet, all he does is slightly deform and start to bounce back out into his little bear shape. Next up, I'm going to be taking the candies and attempting to stretch them to show another part of their elastic properties. Again, I'll start with our coated gumball. As you can see, you can't stretch it. Since it's a hard-coated candy, there is no way to deform it. Our Lifesaver, which is a hard candy as well, also cannot be stretched or deformed. Take our stick gum, and when I pull on this one, it snaps apart. We'll take our taffy, pulling on this one also causes it to snap apart. With our licorice, pulling on it just causes it to keep stretching. And then with our gummy bear, pulling on him also causes him to stretch. Next up, I'm going to be testing each of the candies for their properties when it comes to abrasion. I'm going to be using a spatula to try to scratch and saw at the surface. So when I take my hard-coated gumball, you can see that the surface is a blue color, and when I go ahead and keep scratching at it, I'm slowly chipping away at that colored coating. I have worn a white gouge on the surface of the gumball. With the gummy bear, there is not much I can really do for its abrasion. When trying to cut at it or saw at it, it just keeps deforming and coming back to its original shape. Still a normal gummy bear. For the Lifesaver, starting out with a white surface, and as you can see, I have managed to slowly saw the surface off of it. So it is quite similar to our coated gumball. Now with the stick gum, upon sawing, it is somewhat similar to the gummy bear. It deforms and peels up and falls off in large clumps. So it is a mixture between the gummy bear, which retains its elasticity, and our hard candy, which ends up losing its coating. For the licorice, since it is very dry, some small chunks are coming off, but not much. It is quite resilient, and it just ends up deforming very similarly to the gummy bear. Now to our taffy. Upon sawing at the taffy, it is totally resistant. I'm able to saw a little bit of the edge off, but when working on the large chunk of the body, nothing has happened. Now I'm going to be testing the effects of temperature on the candy. I have here a hot water bath and a cup filled with dry ice to see what happens to their properties when affected by heat. Start off with the coated gumball. It starts to lose its colored coating. As you can see, it started off blue, and now it has turned almost completely white. Also has become very squishy. Next up, I'm going to be taking another gumball, putting it into our dry ice to see what happens when it gets chilled. And while I'm waiting for that to cool down, I will take our hard candy, I will put it in the hot water, and it will be hard to see now since it's clouding up, but the candy is actually dissolving slowly into the water. It is dissolved quite thoroughly, and now that it is dissolved, or partially dissolved I should say, it is even more vulnerable to shattering under very, very light stress. Now that the gumball has cooled down, there is actually a small fracture line already present on the surface, and now it doesn't shatter just upon being dropped, but if I leave it in there for slightly longer, I think we can get it to where it will shatter. And again, while we wait for that to cool, I will take the stick gum, put it into the hot water, and being heated slightly, it is now very elastic, and it can actually be pulled apart into little strands. Now that our gumball has sat in the dry ice bath for a while, I'll take it and drop it from above, and it fractured upon impact. I can now take our hard candy, place it in the dry ice, as well as our stick gum. With that then, I will continue with the hot water bath by using licorice. So again, our licorice, rather flexible, somewhat stretchy, placing it into the hot water bath. Now that it's been heated, it is very stretchy, somewhat dissolved, and deforms very easily. I can now pull it apart just by my hands. Now I will go ahead and take the stick gum out of the dry ice bath, and it is very brittle now. It fractures upon the slightest pressure being applied to it, as well with our hard candy. It also fractures upon being dropped from above. I will take a piece of licorice, add it to the dry ice bath, then I will take the taffy, put it into our water bath. Now as you see, the color coating is also starting to come off from the taffy, turning our solution, or our water, very green. And then reaching in to get the taffy, pulls apart very easily and dissolves rather rapidly because I am only left with a very, very small chunk of taffy. If I leave it in there, I'm sure it will dissolve completely. I have refreshed the hot water bath because obviously after I had put the taffy in, the solution was entirely cloudy because it had turned green. So then now I can take my gummy bear, put it into the water, and then as well I will take out my licorice. And now the licorice, after sitting, is very hard, it is no longer elastic, and it cannot bend. It just simply shatters upon force being applied. I will also take a gummy bear, add it to our dry ice bath. And now the heated gummy bear is very droopy, very elastic. I can barely hold him with my tongs. As you can see, he's actually, just with gravity, falling apart. And now that the gummy bear is sat in the dry ice bath, it is very hard, and in fact shatters when I hit it with the hammer. The first polymer we will be making today is polystyrene, which for that we require styrene, benzoyl peroxide, and toluene. I'm going to start by measuring out 3 milliliters of toluene in my 10 milliliter graduated cylinder. I have 3 milliliters here, measuring by the meniscus. I'm going to take that and add that. Next, I'm going to need my styrene, and I'm going to be adding 1 milliliter of this, or 20 drops, since this is in a dropper bottle. I've just added 20 drops, and now I'm going to need 0.1 grams of benzoyl peroxide, and I have actually already pre-measured that in my weigh boat right here. And I'm going to take this and add it to the solution. And with that done, Right here is my solution. Next step, I'm going to take this and put it in a boiling water bath for 1 hour. So here we have our boiling water bath. I'm going to take my polystyrene mixture that I just made. I'm going to take it and let it sit in the boiling bath for 1 hour. Here is our polystyrene that we have been heating for an hour. I have just turned off the hot plate, and now I'm going to be taking our test tube of polystyrene, setting it into my test tube rack, and I'm going to let this solution cool to where I can handle it in order to continue. So here I have my polystyrene that I have heated and allowed to cool. As you note, the solution is not very viscous. It's about the same viscosity as water. So now I have here a beaker containing 25 milliliters of methanol. I'm going to take my glass stir rod and pour my styrene solution into the methanol and stir constantly. As you see, our solution methanol and styrene has turned milky white. That is the precipitate forming. So now I'm going to take that, and I'm going to filter this through my Buchner funnel in order to collect the precipitate. Once my Buchner funnel has gone and pulled through all the methanol, I'm going to take 5 more milliliters of methanol, pour it into my beaker to wash some of the precipitate out, and then I'm going to pour into my Buchner funnel again. Now that it is dry again, I'm going to take one last wash of 5 milliliters of methanol and repeat the same. Pour into my beaker to wash the beaker, gather as much precipitate as I can, and then pour it into my Buchner funnel, wash and gather my precipitate. And now that I have done both my washes and my filter paper is dry, I will turn off my vacuum, take my funnel off, and as you can see, I have a small chunk of my precipitate on the filter paper. I will take this out. I'm going to be placing it onto a paper towel, and I will gather the precipitate to dry. So here I have my hot water bath. I have collected my styrene precipitate in this test tube, and I'm going to be heating it. I will place it in my hot water bath and let it heat and melt. My small amount of product has melted in the hot water bath, and I'm going to be taking my glass stirring rod, dipping it inside. I'm getting a small string to form inside my test tube. However, I am not able to get it long enough to pull out from the test tube. So as you see, I was able to create polystyrene. The properties of it are somewhat similar to our nylon rope. It is able to stretch relatively far, but it will snap once it gets too thin. And I have several wispy hairs on the end of my glass stirring rod. And the solution itself, now that it is melted, is very viscous. It barely moves inside the test tube, even when I hold it upside down. So here we have our styrene, and now that it has sat and cooled, we can take and pull the strands of styrene up with our glass rod, and as you can see, it is incredibly stretchy, and as you can see, we have several very long strands of styrene now. And if I take it, when I try to pull at it, I stretch it a bit too far, and it slowly breaks the strands. The next polymer we are making is polysulfide rubber. For that, we are going to need 2.5 molar or 10% sodium hydroxide. We are going to need sulfur, 1,2-dichloroethane, and aliquot 336. With that, first, I will start with 20 milliliters of sodium hydroxide. I have already pre-measured that in my 100 milliliter graduated cylinder. I'm going to be taking that and boiling it, so I'll have it in my beaker here. Now I'll come back once this is boiling. Next I'm going to be adding sulfur to the sodium hydroxide. I'm going to be adding 1.8 grams of sulfur into this, and it is going to be stirred into the solution until it is completely dissolved, which may take up to 10 to 20 minutes. After about 20 minutes, our sulfur solution looks like this. It is thoroughly dissolved. I have removed my stir bar from the solution. Now I'm going to be dividing the solution equally into two identical beakers. I have about 5 milliliters in each beaker. Now I need to test to make sure that the temperature is below 70 degrees Celsius. I am adding half a milliliter of aliquot 336 to one of the beakers. And then we are going to be adding 2 milliliters of dichloroethane to each of them. And now we are going to stir them. We have a very nice precipitate forming in our solution. Now with that then, we want to discard our aqueous solution into our waste container. In the beaker without the aliquot 336 catalyst, no precipitate has formed. It is just solution. Because of that, you're just going to discard it to waste. Now I'm going to be washing the precipitate with DI water. Now that it's been washed, I can take out the precipitate, place it on my paper towel, and roll into a ball. Now that I've formed it into a little ball, you can see that it bounces. Now I'm going to take our rubber ball. We showed that it was bouncy. Now I'm going to take it. As you can see, we can stretch it out. Next, we are going to be preparing nylon. So first of all, I'm going to be using hexamethyldiamine and sebacoyl chloride. I'm going to take 3 milliliters of hexamethyldiamine into this beaker. And then I'm going to be taking 3 milliliters of sebacoyl chloride into this beaker. And now that I have my two solutions, I'm going to be taking the sebacoyl chloride and pouring it down the side of this beaker very slowly. Now that I have done that, you can see that I have 2 layers in my solution, and right in the middle there's an interface between the 2 layers. This is important because now I can take my tweezers, bring them down into the interface and pinch, and I can start to pull up on my nylon strand. Now I'll bring in my stir rod, so my strand just broke. Now I can take it and I will first rinse it with some water. Now that I have washed it, I can take it and lay it onto my paper towel. And now we have a string of nylon. Now we are going to examine our nylon string, so I can take the strand up, and first I'm going to test its stretchiness. So I have it in both of my hands, and as you can see, I can stretch the strand quite a bit until it snaps. And again, a small strand. I can pull it apart. There is not much you can do pressure-wise to deform it. If I hold the strand out, you can press on it and it very quickly bounces right back into shape. It does not have any form of permanent elastic deformation. Now I've taken and prepared a small ball out of my nylon string, and to demonstrate, it does not bounce at all. Now I can take my nylon ball, and if I slowly unfurl it, I can get my strand back, and then if I stretch it, it is just like before, stretches quite a ways, and then finally breaks into two fibers. So here I have my hexamethylene-diamine and sebacoyl chloride mixture. You can see that the interface is still there, so we have our two layers. I'm now going to take my stir rod and vigorously stir the solution to make as much of the nylon as possible on my stir rod. Now I can take this solution and decant it off into my wash bin. And now I'm going to take my nylon, and first I'm going to wash it with 50% ethanol, and I want to wash this very thoroughly. And then next I'm going to be using my distilled water. And now that I have thoroughly washed my nylon, I will take it and leave it to dry on my paper towel. Once my ball of nylon is dry, I'm going to be taking a small part of it, putting it inside my test tube right here, and I'm going to be heating the test tube with the nylon in a hot water bath. So here I have my hot water bath. I'm going to be taking my now dry chunk of nylon. I'm just going to be tearing off a small portion of it. I'm going to be adding it to my test tube. I'm going to place this inside the hot water bath and wait for it to melt. So here I have my nylon sample. We have tried to heat this in a boiling water bath for about a half hour, and it was not melting. So now I'm going to take it, put it into my Bunsen burner, and try to get this to melt. So here I have my original nylon string that I made by pulling up from the interface. As we noted, it is quite stretchy, but it does not have any form of bounce to it when rolled into a ball. This is another nylon clump that we made, and again, does not bounce, so it shares properties exactly the same as the first nylon string. When we heated it in a hot water bath, we were not able to get any form of a melt to happen. When we moved to try to heat it in a Bunsen burner, it denatured and heated so rapidly that we were not able to get any form of a string out of it. We are only left with a gooey coating on our glass rod. And then we have our styrene that we made over here, which you can see the wispy strings left on the glass stirring rod for when we pulled it out. It is a very viscous substance still left inside the test tube, and as we saw, it is also able to be stretched very similarly to our nylon. And that is all of our polymers. So here we have our nylon chunk that we made. After boiling it for a half hour in hot water, we were not able to get it to melt. So now I'm going to take it and put it very gently into the Bunsen burner flame here. We don't want to heat it too much, too rapidly. So I'm just going to hold it right on the top of the flame. Now I'm going to take my glass stirring rod, now that we've heated it, to try to see if I can get a strand to come off of it. I cannot, so we will continue heating. Now that we've heated it some more, I will try again. And again, no strand. Now Now we are going to be making polyesters. These four chemicals are all we are going to need to start. We have phthalic anhydride, sodium acetate anhydrous, glycerin or glycerol, and ethylene glycol. Here I have my 2 test tubes that I'll be using to create my mixture and solution for polyester. In this weigh boat, I have 2 grams of phthalic anhydride already weighed out. I'll add that first to one test tube. I have a second one also weighed out at 2 grams of phthalic anhydride. I will pour that into the other test tube. So we have our 2 test tubes containing phthalic anhydride. I have my sodium acetate anhydrous. Again, I have pre-weighed 0.1 grams of sodium acetate into these 2 weigh boats. I'll now be adding that, 1 to each of the test tubes. Next, I will be taking my glycerin or glycerol along with ethylene glycol, and I'll be adding 0.8 milliliters to one of the test tubes. Since we know that 1 milliliter is 20 drops, we can then use our math to say 16 drops of each will be our 0.8 milliliters. Now first I'm going to start with my glycerin or glycerol, and I want to add my 16 drops to only one of the test tubes. I will use this one. Here I will label it, that way I know which is which. So this is my glycerol. Next is my ethylene glycol. Again, 16 drops, but this time it will be added to the opposite test tube. The glycerin is very viscous and is actually stuck right about here in the test tube. It's not able to go all the way down. It is going to take some time. However, our ethylene glycol is not nearly as viscous and is able to go almost all the way to the bottom of the tube immediately. Okay, here we are with our polyesters. In this tube, I have my 2 solids with ethylene glycol. The one next to it contains the 2 solids, but it is the one that contains glycerol. We have clamped them together like this. They are angled back and away from us towards the back of the hood that we are working in. We are working in a large hood, that way you are able to see exactly what we are doing. They are clamped high up towards the mouth, that way we are not heating this clamp when we use our Bunsen burner. And as well, they are clamped very tight. You can see I can slightly move them as they are now, which means I need to get it just a little tighter. Starting the Bunsen burner. And we have our cone that is sitting at about this height. So I'm going to now take my tubes, rotate them to where they will be heated just above the cone of the flame. And I am taking and adjusting the tubes because I do not want them to heat too rapidly. I don't want the solutions to boil, I just want them to heat evenly. As you can see, we are getting bubbles to form in the solution containing glycerol. The bubbles are actually moisture escaping the solution. And now our solution of ethylene glycol, it is now entirely into solution. And so now I'm just going to be heating these for about 5 minutes. You can start to see that our glycerol solution is starting to become yellow. And now I am just manually moving the Bunsen burner in order to heat exactly where I want. Now 5 minutes have passed, so So I'm going to take my two solutions here. The one containing ethylene glycol is a red or orange hue, and our one containing glycerol has turned brown, almost black. Now I will let these two solutions sit and cool. So here I have my two solutions once they have cooled. Right here on my left we have the glycerol solution. Here on my right we have the solution that contained ethylene glycol. If I tilt it to the side, note that it is a very red hue as well, and it is a very viscous solution. Barely starting to flow on the side. So after waiting here for even just a little bit, it barely moves. And then here with our glycerol, tilting to the side, it does not flow whatsoever. It is entirely solid. So we have our ethylene glycol as a viscous solution, and our glycerol has hardened completely. Now I'm going to take a glass stir rod, I'll poke at my glycerol solution. Hard as I expect. And there are some fibers actually in here that are very brittle. When my glass rod comes into contact with them, they break immediately. With my ethylene glycol solution. And as I press, it deforms actually, and I can get some of it to come up with my glass stir rod. Even more evidence of a very viscous solution rather than a complete solid. Here I have my glass stir rod that I put into my ethylene glycol and pulled a string out of it. And as you can see, it is actually snapped because it is incredibly brittle once it cools. Even right now, just the slightest little bit of pressure immediately snapped that strand. In this last part, I'm going to be taking 4% sodium borate and mixing it with 2% polyvinyl alcohol, or PVA. I have 5 milliliters of the sodium borate and 50 milliliters of the polyvinyl alcohol. And upon stirring these together, I get a slime-like substance. I'm going to take this, pour it out onto my bench top here. That way I can manipulate it by hand. And as you see, it is quite sticky, has quite a bit of elasticity. I can stretch it for quite a ways before it finally pulls apart. And whenever it gets deformed, it will slowly just combine back together into a blob. Scratching at its surface with the stick really doesn't change it. It sticks to the stick, so it rolls along with it, but it won't cut unless I put a lot of force behind it. All in all, it is just a very, very slimy substance. So after this lab, all of our equipment is coated with some form of a polymer. So in order to clean them, I'm going to be using xylenes. So right here on this glass stirring rod, I have some nylon. So I'm just going to add xylenes to it, stir around, and then take my paper towel, dry it off, and as you can see, I now have a very clear, clean glass rod with no trace of nylon on it. Here we have a glass rod from our styrene, again, just using xylenes, soak the end of it, take our paper towel, nice clean end of the glass rod. Here I have 3 test tubes. These first 2 contain some remnants of when we were trying to heat and melt the nylon. This one contains our polystyrene. Using xylenes, I'll just add a little bit to each of the test tubes. I'll take my test tube scrubber and we have eliminated almost all traces of the polystyrene. I'll just add a little more xylenes and scrub one last time with the test tube brush in order to get all of the polystyrene out of my test tube. And then I can rinse this with water just to make sure that everything is gone. As well now, our 2 nylons. I can invert them as well to try to dissolve the nylon, and then take my brush. As you can see, these ones will still take a bit more thorough cleaning.